The Istanbul Airport project stands as a testament to modern engineering and ambitious planning, positioning itself as one of the largest and most significant airport developments in the world. This colossal undertaking aims not only to alleviate the congestion at Istanbul Ataturk Airport but also to establish Istanbul as a major global aviation hub. The new airport is strategically located approximately 35 kilometers, about 22 miles, from the old airport, offering ample space for expansion and accommodating the rising demands of air travel. Situated along the Black Sea coast, this site is not only geographically advantageous but also positioned to leverage Istanbul's unique position as a bridge between Europe and Asia. The construction of Istanbul Airport is divided into 4 distinct phases, with the entire project projected to reach completion by 2027. Each stage is meticulously planned to ensure that the airport can begin operations even before the final phase is completed, thus minimizing disruption and maximizing economic impact. The timeline reflects a commitment to rapid development, with an emphasis on efficiency and coordination among various contractors and governmental agencies. This structure allows for ongoing assessments and adjustments to the project as it unfolds, ensuring that all aspects are executed flawlessly. The financial scope of the Istanbul Airport project is monumental, with an estimated total cost of around €12 billion, approximately $14.25 billion. The economic implications of this investment extend far beyond the construction phase. Once operational, the airport is expected to generate significant revenue through passenger traffic, cargo operations, and various commercial activities. The construction process of Istanbul Airport is a remarkable feat of modern engineering, characterized by massive excavation and infrastructure development. During the construction phase, approximately 700,000 cubic meters of soil are excavated every day, with a fleet of 1,453 trucks facilitating the transportation of this earth. This monumental task requires meticulous planning and coordination to ensure that operations run smoothly and efficiently. Over the duration of the project, it is anticipated that around 750 million cubic meters of soil will be excavated. In addition to excavation, a staggering 7 million cubic meters of concrete will be poured to form the airport's foundations and structural elements. This emphasis on robust infrastructure is essential for accommodating the heavy aircraft traffic expected at the airport and ensuring the safety and longevity of the facilities. The construction is further augmented by the use of advanced technologies and machinery, enabling rapid progress while maintaining high safety standards. Continuous monitoring and assessment during the construction phase ensure that any potential issues are addressed promptly, minimizing delays and maintaining project timelines. The first phase of Istanbul Airport's construction was completed in a record time of just 42 months, from June 2014 to October 2018. This rapid turnaround is a testament to the efficient project management and the dedication of thousands of workers involved in the construction. The initial phase of the airport boasts a state-of-the-art terminal designed to handle an impressive annual passenger capacity of 90 million. With a total area of 1.4 million square meters, approximately 15 million square feet, this terminal is recognized as the largest airport terminal in the world under a single roof. This expansive design allows for the seamless processing of passengers and efficient management of operations, setting a new benchmark for global airport facilities. The terminal's layout is meticulously designed to enhance passenger flow and experience, with amenities and services integrated throughout the facility. From check-in to boarding, every aspect is tailored to provide a comfortable and efficient travel experience. The airport's architecture incorporates elements of Turkish culture, creating a unique and welcoming environment for travelers from around the globe. Istanbul Airport's Air Traffic Control Tower, a masterpiece by Pininfarina and AECOM, stands as both a beacon of innovation and a tribute to Turkish heritage. Rising an impressive 90 meters, 295 feet, above ground, and spanning around 6,085 square meters, 65,500 square feet, it is the largest airport control tower in the world, with a striking 360-degree panoramic view. The tower's tulip-inspired design, symbolizing Istanbul's cultural legacy, weaves together influences from aerospace and automotive engineering with Turkish artistry. With its sleek, aerodynamic form, this remarkable structure catches the eye of travelers from Europe to Asia, embodying both elegance and functionality. Istanbul Airport covers a staggering area of 76.5 million square meters, approximately 29.5 square miles, making it one of the largest airport developments globally. The expansive site provides ample room for various facilities, including passenger terminals, cargo handling areas, and maintenance operations. The sheer size of the airport is indicative of its ambition to handle an enormous volume of air traffic and provide a comprehensive range of services. In the first phase, Istanbul Airport features 5 runways, ranging from 3,060 meters to 4,100 meters, approximately 10,000 to 13,450 feet, in length. These runways are designed to accommodate a wide variety of aircraft, from smaller regional jets to large international airliners. The strategic layout of the runways ensures efficient takeoff and landing operations, minimizing delays and optimizing air traffic management. The capacity of the runways is complemented by advanced taxiways that facilitate smooth movement between runways and terminal areas. This comprehensive runway and taxiway system enhances the airport's overall operational efficiency, allowing it to handle a high volume of flights and minimize congestion. This vast area allows for future expansions, ensuring that the airport can adapt to the evolving needs of air travel. The planning phase included extensive environmental assessments and land usage studies to maximize efficiency while minimizing ecological impact. The location's proximity to transportation networks, such as highways and rail systems, further enhances the accessibility and utility of the airport. Istanbul Airport is equipped with an advanced baggage handling system that stretches 42 kilometers and is capable of processing nearly 30,000 bags per hour. This sophisticated system utilizes state-of-the-art technology to ensure efficient handling of luggage, significantly reducing wait times for passengers and minimizing the for lost bags. The baggage handling infrastructure includes early baggage storage capabilities, allowing for seamless integration of arriving and departing flights. This level of efficiency not only enhances the passenger experience but also contributes to the airport's overall operational effectiveness. One of the most significant benefits of the Istanbul Airport project is its potential to create jobs for the local population. It is projected that the construction and subsequent operations will generate approximately 225,000 jobs, spanning various sectors including construction, airport management, retail, and hospitality. This influx of employment opportunities is critical for the local economy, providing a substantial boost to livelihoods and the overall standard of living in the region. Job creation is not only limited to the construction phase. Once the airport becomes operational, numerous positions will be available in areas such as customer service, security, maintenance, and logistics. The airport's influence on job growth aligns with broader economic goals, positioning Istanbul as a vibrant center for international trade and travel. The construction of Istanbul Airport represents a landmark achievement in aviation infrastructure. With its strategic location, extensive planning, and substantial financial investment, the airport is poised to become one of the busiest and most important aviation hubs in the world. Each phase of the project is meticulously designed to enhance the efficiency and capacity of air travel while creating numerous employment opportunities for the local population. In this fourth part of the bridge installation at the Kildrecht Lock, these massive bascule bridges, designed for both road and rail traffic, were custom-built in China, alongside the enormous lock doors, and were transported together by sea to the port of Antwerp. Once in Antwerp, the unloading process begins with separating the bridge from the ship. A specialized vehicle, called a Kamag, a heavy-duty transporter capable of carrying substantial loads, is then driven onto the pontoon. Each of these bascule bridges weighs a staggering 2,000 tons, and the hydraulics used to lift the bridge must be incredibly robust and finely tuned. This Kamag will play a key role in transporting the bridge to the next stage, where it is aligned with hydraulic jacks to be lifted. After the successful unloading, the bridge embarks on a journey across the Waasland Canal toward its final location, at the Kildrecht Lock. However, this is not a straightforward route. Due to a protective embankment that separates the lock complex from the main dock, the convoy, including tugboats and a powerful towboat, must navigate a complex route that crosses multiple waterways, lock systems, and narrow passages. Moving such a colossal load through these waterways is an engineering challenge in itself. Once the convoy arrives at the Keeldrecht lock, the bridge and its support equipment are carefully anchored and further stabilized in preparation for final installation. To prevent any chance of collapse due to hydraulic failure, heavy-duty steel blocks are positioned around the hydraulic jacks. These serve as additional safeguards, ensuring that even under extreme load, the bridge remains securely in place. The K-Mag's wheels are then rotated to a 45-degree angle, enabling it to pivot the bridge by 90 degrees to align perfectly with the lock's infrastructure. This level of flexibility is crucial, as any misalignment at this stage could result in significant delays and potential structural issues later on. Once the bridge is rotated and aligned, hydraulic jack lift it to the designated height, ready for further modifications and the final steps of the installation process. With the bridge positioned correctly, engineers prepare to insert massive steel axles into pre-drilled holes on either side of the bridge. These axles, each weighing around 55 tons, are essential for the bridge's functionality and must be installed with absolute precision. To facilitate the fitting, each axle is cooled in a specialized chamber to around 10 degrees Celsius. This cooling causes the axle to contract slightly, allowing it to slide more easily into the fitting without forcing. Simultaneously, the bridge's steel around the axle holes is heated to approximately 110 degrees Celsius, causing the metal to expand temporarily. This combination of cooling and heating allows the axle to slip into place smoothly. Inside the torsion tube, a hydraulic pump slowly draws the axle inward in a single, continuous motion to avoid any misalignment. Once the axle is in place, the metal around it contracts as it cools, while the axle itself expands as it warms up to ambient temperature. This dual effect creates an ultra-tight fit, ensuring the axle and bridge remain inseparable. This is a key aspect of the installation, as the bridge must withstand enormous loads without any potential for slippage or movement. Advanced hydraulic systems and final calibration. With the bridge's main components in place, hydraulic systems are installed to manage its movement. These hydraulics are exceptionally powerful, designed to lift and lower the bridge on demand with precision and reliability. Engineers attach multiple circuits to the hydraulic system, enabling independent control over each component. This ensures that even if one section of the system requires maintenance or fails, the other sections can continue functioning, preventing potential disruptions. The next phase involves preparing the bridge's counterweight to ensure it remains balanced during opening and closing. For this, a combination of 1,780 tons of concrete and an additional 72 cranes, one with a 700-ton capacity and another with a 500-ton capacity, are used to install these beams with meticulous coordination. Even the smallest misalignment could compromise the bridge's stability, so each beam is positioned with extreme care. Tons of steel plates are added to specific sections of the bridge. These counterweights help stabilize the bridge and prevent unnecessary strain on its moving components. The bridge deck is thoroughly cleaned, and a durable, wear-resistant layer is applied to its surface to accommodate the heavy traffic expected once it is operational. Prefabricated concrete beams are placed across the bridge, reinforcing its structural integrity and providing support for the road and rail infrastructure that will run across it. To test the bridge's movement, the hydraulics are engaged, raising the bridge to a vertical position. This test confirms that the bridge can achieve full clearance, allowing large container ships and high-structure vessels to pass through the lock. Load. Testing and final inspections. Before the bridge opens to public traffic, it undergoes rigorous load testing to ensure it can handle the demands of regular operation. Engineers place the bridge under various load scenarios, measuring deflection and elasticity to ensure these values match the engineering calculations and meet regulatory standards. During this testing, topographic surveyors measure the bridge's response to loads as heavy as 70 tons, comparing each movement to initial baseline measurements. These detailed inspections verify that the bridge's deflection is within acceptable limits, which is typically no more than a few centimeters. The bridge passes all inspections, and final adjustments are made to ensure its mechanisms operate smoothly. After months of meticulous planning, engineering, and installation, the bridge is finally ready for public use, much to the relief of the truck drivers and commuters who have been eagerly awaiting its completion. This project exemplifies the highest standards in modern engineering and highlights the extraordinary skills and coordination required to bring such a massive structure to life. The Kieldrecht Lock Bridge now stands as a symbol of both technical prowess and innovative design, ready to serve the heavy maritime traffic that navigates Belgium's waterways.